Coming back to our textbook for a minute, here's the skill that we want to get good at over the next half a class. That is to take a couple of polynomials and add them together and simplify the result. And we're going to work on building several different approaches for how to do this. Let's start by just focusing on the first of these examples. This is example 628 from section 6.2. So before we get to the example, let me ask you about each of these polynomials individually. So the first polynomial, 5x to the third plus 4x squared minus 6x. What's the degree of this polynomial? It's 3, the highest exponent of any of its terms. How about the second polynomial, minus 3x squared plus 9x minus 2? Its degree is 2. Great. So here's a question. If I add these two polynomials together, what do you think the degree of my answer is going to be? So there are three different methods that people talk about for adding, subtracting, multiplying polynomials. Actually, maybe I'll go a step further than that. I'm going to say there's 4 different approaches. And I want to use this example to kind of illustrate each of the 4. So let me name them really quickly before we talk about them. There's a method called the horizontal method. I think this tends to be the default that a lot of textbooks tend to use for how to do this. But if you doll up the horizontal method a little bit, you can also make something called a vertical method. And then if you want to get fancier, there are also ways of translating this into, I'm going to call this, it's going to be weird for it to come out of my mouth. I'm going to call this the traditional algorithm. And I think you'll understand why when we actually look at this method. Because what the traditional algorithm is going to do is it's going to let us draw an analogy between adding and subtracting polynomials and adding and subtracting multi-digit numbers, that process that you learn how to do in 2nd or 3rd grade. Right? So traditional algorithm makes that comparison. And then also the 4th method is also an analogy, but it's an analogy to what is often called the new math way of adding or subtracting. It's called the lattice method. Lattice method, I don't think we have an analogy for in adding and subtracting, but when we get to multiplying polynomials, the lattice method will be something that we have a chance to do. So I'm just going to write that as a multiplication only kind of method. So we won't get to see it on this example, but we'll get to see it a couple examples from now. Let's start with the method that most authors of algebra textbooks cling to for how to add two polynomials using a horizontal method. So if I look at these two polynomials, what am I thinking about? What's the first thing I'm going to be looking to combine together if I'm going to add these two polynomials? What do you think? And just replace the English in this problem statement with arithmetic. In other words, add this first polynomial plus this second polynomial. That's what it's asking us to do. So what's the first thing that you want to do here? What's the first thing that comes to mind? So the most important consideration in adding or subtracting polynomials is that the engine of adding and subtracting is like terms. Okay? We can only combine together and make simpler a sum or a difference of two terms that are like terms. And how do we know what the like terms are? Give me an example of a pair of like terms in this addition problem.
So it would be negative 6x and 9x.
Okay, how do you know those are like terms?
So they have, well, they don't have the same coefficient, but they don't have any exponents.
Yeah, right. In fact, one of the ways of spotting like terms is that the coefficients are the only things that might be different. Everything else about those terms needs to be the same. Right? So the variable factors, the efficients, if we like, those need to be the same, and that's what makes like terms like. Right, so when you look at both of these, they both have a variable factor of x and no exponent written in, so what is the secret exponent? 1. Right, both of them have a variable factor of x to the first power. That makes the two of them like terms. And so how then do I combine negative 6x plus 9x? How do I combine negative 6x plus 9x? How many x's do I get? Yeah. The way that we combine like terms is by a process of reversing the distributive property of multiplication over addition to rewrite, instead of multiplying by x first and then adding the results, we're instead going to add first and then multiply the result by x. The distributive property says that those operations are the same. So all I'm really doing when I'm combining like terms is I am adding the coefficients. Negative 6 plus 9 gives me 3. And so when I combine that pair of like terms together, I end up with 3x. Is there another pair of like terms in this addition problem that I can combine?
4x squared and negative 3x squared.
4x squared and negative 3x squared. Yep. There's another pair of like terms. They're like terms because the only thing that's different about them is the coefficient. The variable factor is the same, x to the power 2. Same variable, same exponent. Right? So we can combine those together. Plus 4x squared minus 3x squared. So how many x squareds do I end up with? I end up with one of them. Notice, too, that when we combine like terms, the coefficients combine, but the variable factors remain the same, right? I combine two x squareds by adding them together. I get something which also has an x squared. I combine two terms that both have the like factor of x in it, and I get something which has the factor of x in it. So my exponents are not changing in the process of combining like terms, and they never will. I like to make the analogy that it's like having 4 $100 bills in a stack and then taking away 3 $100 bills out of that stack. What do I have left? I have one $100 bill. The denomination has not changed. Just like when we were adding fractions with common denominators, the denominator remained the same even if the numerator, the number of them that we have, was changing. Same thing with like terms. So we found two pairs of like terms that we can combine together in this example. What happens to the other stuff? The 5x to the third and the minus 2? Yeah, it just stays the same. They don't have anything to combine with, and so they just become a part of the window dressing, but they're an important part of the window dressing. 5x to the third plus 3x plus 1x squared minus 2. And once we've gotten to a place where we no longer have any more like terms that we can combine, that's when we know that we're done. Right? We can't add together any of the terms that are left because we have no like terms. Remember, like terms are the only kinds of terms where we can simplify their sum or their difference into a single term. And we don't have any like terms here, so we've got to be done. At this stage in the game, when we're adding or subtracting polynomials together, because the only consideration we have is like terms, like terms, like terms. Exponents do not change at all when we're adding and subtracting. Another reason for that is that we have a whole catalog of ways in which exponents do change. But all of those require us to be multiplying monomials together, dividing monomials by one another, raising monomials to more powers, or distributing exponents across multiplication. None of that is happening in the problems where we're only adding or subtracting polynomials. Our list here never got past the D in PEMDAS. And so down at the A and the S level, exponents don't change. They remain the same because they're the currency, they're the common denominator, if you like, of all the like terms that we're adding together. So it remains the same. I added together a polynomial of degree 3 plus a polynomial of degree 2, and my answer was a polynomial of degree 3, and not 5, because the exponents don't change when we add or subtract polynomials, right? All we do is combine like terms by adding or subtracting their coefficients, however the original problem was written. The only other thing that some authors will do with an answer like this is that they often will rewrite the answer in a way that makes the degrees of the monomials decrease as we go from left to right. They call it writing it in descending order and decreasing order. So for that, all they would do is trade places between this term and that term. So if I were to do that, and this is not a necessary step, but depending on what else you're doing with these polynomials later in life, this may be a step worth doing. Just rewrite it so that the exponents decrease as you read from right to left. Also, this coefficient of 1 sitting out in front of the x squared, because multiplying a quantity by 1 is an invisible operation, we can also get rid of the 1 and just write x squared. And that, then, is as simple as we could possibly hope to make our answer. It's not that last step of writing it in descending order and erasing the ones. That's not something I'm going to dock you on if you don't do. But just for the sake of being easier on the eyes and also easier to do anything with later on, it's a good practice to get into. So the other two methods for addition or subtraction of polynomials are obviously going to be doing the same kind of algebra. They're just arranging your thoughts in a different way. So the way that the vertical method works is it takes the terms from my first polynomial, let's write them out, 5x to the power 3 plus 4x to the power 2 minus 6x. Write them all on a line. And then take the terms of the second polynomial and write them underneath the terms of the first one. And when you do that, you want to take pains to line up the like terms above one another. So when I write this first term, minus 3x squared, I want to write it underneath the term to which it is a like term. So I should write it underneath the 4x squared when I use the vertical method. So you're doing a little bit of extra work up front to think about like terms. So the minus 3x squared I'll put right there. The plus 9x I'll put underneath its like term. And then the minus 2, well, it doesn't have a like term, so I'll just put it out here in empty space. And the idea now is that what I'm doing is adding. And because I've lined up my like terms right above one another, that means that I can laser focus in the columns. And when I add my 5x to the third, well, it doesn't have a like term to add to, so I'll just drop it right down, 5x to the third. But meanwhile, my x squareds, when I add them, they're right above one another, and I can see that because I've taken the time to arrange them in vertical columns. Now I know that I want to add the x squareds from here for the x squareds from here, and the 4 plus negative 3 adds together to give me plus 1. And then the x squared carries down because it's the like term. It's the factor of the like term. Ditto for my x to the power 1s. I've already arranged them above one another. So the factor, x, carries down, and the coefficient, negative 6 plus 9, becomes positive 3. And then my minus 2 doesn't have anything to add to, and so it just carries down by itself. And again, we've arrived at the same answer that we got using the horizontal method, but we kind of front-loaded the work of organizing our two summands and aligning the like terms into columns. And that's what we call the vertical method. Same work, same algebra, just organized in a different way. I happen to like the vertical method a lot myself. One of the reasons that I really like it is what we'll talk about next, which is that this algorithm that we just used calls to mind a very familiar process from second and third grade. When you first learn how to add multi-digit numbers, you do the same sort of thing. Right? The analogy is if I wanted to add the number 5,460 to the number 392, if I wanted to add that without using a calculator, what would I do? Yeah, I would put the 392 underneath the 5460, taking care to align the digits that have the same place value as one another. Right? So the 1's digits, 0 and 2, are above one another. The 10's digits are 6 and 9. The 100's digits are 4 and 3. And then there's a 5, which is a 1,000's digit out there that doesn't have a partner underneath it. And then once I've aligned these numbers above one another according to the place values of their digits, then what do I do to actually carry out the addition? I just add directly down the column. 0 plus 2, and then 6 plus 9. And then when I add the 6 plus 9, I get this 15, and so I have to do this funny carrying process that you learn when you learn this algorithm for the first time. You carry the 1 over to the next column because it's secretly a hundreds digit, and then I add 1 plus 4 plus 3. That's going to give me an 8. And then the 5 doesn't have anything to combine with, and so it just drops down. And so at the end of the day, we end up with this multi-digit number, 5852. Right? The very same process that we just used to arrange our two polynomials into columns and then just add directly down those columns. Like terms add together with one another for the same reason that digits with the same place value add together in the columns when we add using the traditional addition algorithm. And so what the traditional addition algorithm does is it just repackages this vertical method without writing all of the variable factors in here. So if I were to port this over to the traditional algorithm, how I would write it is as 5, 4, -6, 0. So I'm writing how many x to the thirds I have, how many x squareds, how many x to the power 1s, and then how many x to the power 0, which we didn't have any of in our first summand. And then I'll do the same thing with my second polynomial, my x squareds, my x to the power 1s, my x to the power 0s. So this one does have a constant term of -2 coefficient. So I'm just writing the coefficients without writing the variable factors. And then I'm just using our traditional addition algorithm to carry out this addition. The only thing I don't have to do, and this is kind of nice compared to our traditional addition algorithm, is I don't have to worry about carrying the 1 or doing any of that funny stuff. Because unlike in digit arithmetic, it's not possible for us to make something of 1 degree into something of another degree by adding them together. In digit arithmetic, we can have so many hundreds that we end up needing to put an extra 1,000 onto the next column. That doesn't happen here, because combining like terms never changes the degree, never changes the exponent. And so we're never going to move between columns when we add polynomials together. So if I strip out all of the variable factors and just focus on the coefficients, this is what I end up with, 5, 1, 3, -2. Then all I would do to get to my final answer is add my coefficients back, or add my variable factors back in. X to the power 0 on the furthest right one, but that's invisible, so I can just hide it. X to the power 1, which is just an x to the power 2, and x to the power 3. Add in some addition signs where they don't have addition signs, and I'm back to my answer. So all of these roads lead to Rome, and whichever one of these you feel like you want to hang on to is the method that if you can apply it correctly and consistently, that's the one you ought to use every time.